And hello everyone and welcome into yet another live stream. Now, if you would just give me a second, I just have to first of all ping my Discord server because yes, that's what I'm doing right now. I am actually doing these things. Not forgetting. There we go. Science and MKT channel streams at streams. And I missed that stream. I am very upset. I am very upset. I missed the stream. It was 3 hours ago. I woke up 2 hours ago and last. Damn it! I missed the stream. All right. Well, today I'll be doing math. We'll be doing math science and actually interesting math science and math. You see, basically, I have 3 sources which I would like to exploit. Feels a bit wrong to say it, but 3 sources which I would like to exploit. Well, there are 3 chapters. 4 chapters I'm writing all at once, and for 3 of them I have sources. For when it comes to abstraction negative 2, which is quantum physics, I am listening to the wonderful wonderful lecture by Brand Carlson, and it's obviously wonderful. And I made a video about the entire video about quantum physics was pretty much just an ad for this lecture. So amazing 5 videos, because Brand also uploaded some videos after finished the lecture, then came back a few years and uploaded. It's a great lecture. It's amazing. That's where I got all of those. Obviously, I'm modifying it a little bit because otherwise I would be just copying it. So that's kind of would suck. So for example, this thing is not from the lecture. So basically, all the information is from the lecture, but I'm running myself and I'm making my own examples. So this is not from lecture, it's from me. It's a good example. Also, the example which I love and adore, this one. I adore this example. The 2 S's, that's kind of pointless. Also, this is adding. I feel like I genuinely messed it up badly. Very badly. Oh well. Anyhow. So yeah. This shouldn't be redivided by 2 pi because then it doesn't matter. Basically, yes, so I love this one. Obviously, things like these are from the lecture, not writing myself because I can't. This is just a transformation of expected position to the expected velocity operator. And as smart as it sounds, this is just me reading notation. This means expected, this means operator, this means velocity from physics. And if you go through it, it all makes sense. It actually is a rather simple way to solve this kind of equation. If you take a look at it, this is a wave function, right? So expected position, we know that it's this, right? This is the thing. And then, well, we just put the derivative inside to make it a partial. Then we do the, Schrodinger equation trick to change it into this, and now we have partial derivative in relation to x, which is convenient. Then we go on and on, a lot of transformations. So this is my first source, right? The Brand Carlson's lecture is a great source. My second source is for chemistry over here, and it's the book. Which we walked with the book on the streams. It's the book. Once again, a great source. As you can see already, we did a lot of work here with the book. It's good. It's a good source. My third source, which unfortunately I shouldn't redo on stream, is a book. Also a book, except a book to which I do not have the copyright, and a book which is not cheap. It is Grey's Anatomy, one of the newer ones. I don't mean the 100-year-old, because I have the 100-year-old with open, which is practically open source from Google, but this is from a new one. Haven't worked with it in a while, mostly because I don't do it on streams, which means it's a bit more. Oh yeah, because the spelling is different. But neurons are spelled differently. I'm pretty certain this is how they are spelled. With, I think, E, or I remember they were spelled differently. because British, you know. Now, there are the three sources, but there's also a fourth chapter which I'm working on, which I haven't really done on stream yet, which is weird because I should. And that is the math chapter. Math chapter is great, I love math, and right now I'm working on calculus, as you can see. And I dig it, it's great. And let's do calculus, starting with limits. Limits are a start to calculus because limits are basically, well, limit is a single operation which perfectly describes the entire calculus, which is, the entire calculus is just kind of, let's see what happens as a thing approaches infinity or a zero without actually being infinity or a zero, to see what's going on. And limits, that's why limits are the base, limits are that thing. And this is just what are limits, so the specific and possible questions. Yeah, we have a problem like sine x divided by x. If we go over here, Desmos, if we do sine of x divided by x, we can see that as a fine function. It's a fine function, right? It just goes, yeah, it's really smooth, except over here it's undefined, which is weird. I mean, it's rather bizarre. It's undefined at 0, even though it seems so smooth, it seems so fine. Why is it undefined at 0? Well, because if we input 0 over here, sine of 0 is equal to 0, which means we would have 0 divided by 0, which is undefined. So this is a problem. But limits do things differently. When you have a limit, I suppose you cannot have limits in Desmos, unfortunately. When you have a limit, as x approaches 0 of sine of x divided by x, then it is different. Because you can see what the limit is actually approaching. Actually, I just realized that we are missing one thing here. We can, yeah, so we can see what limit is approaching. And here's the thing. There are three basically ways to compute limits. First one is for simple equations, just to input the number. That's it. You just input the number. So x2, just input it over here, there we go. Limit as x approaches 2 of this equation is just equal to 9. That's for simple ones. When it doesn't work, when you get 0 divided by 0, you can use the L'Hopital's rule, which is, its spelling is insane. L'Hopital's rule, like L'Hopital's rule. It's a mouthful, but you can use it. It uses derivatives, and you can solve these equations like that. You can also see what's going. Well, I suppose that's also L'Hopital's rule. So you could use that for complex equations, and then for other equations, which even more complex or just some basic ones, you can use existing definitions, which all have proofs, except I won't get into them for now. The reason why I'm doing first computation and then epsilon delta is because, unlike many other proofs, epsilon delta doesn't actually give you an answer. It really won't give you an answer. Epsilon delta will tell you if the limit is calculable, which means if you first solve a limit like this and then check with epsilon delta, then you will see if this answer is correct. But if you use epsilon delta, you will just only know if this is correct, you won't know what it is. That's why I'm still first starting with this, because it's important, right? This is a normal way to solve limits. Epsilon delta is just over here to prove that that value actually makes sense. In derivatives, I'll go the other way. I'll first explain what are derivatives and their definitions, and only then we'll go for the computing derivatives. Because when it comes to derivatives, we can define them in a way that would already give us a way to calculate the derivative, which is the limit of f of x, a limit of f of x plus h plus f of minus f of x divided by h as h approaches 0. There we go. Yeah. And it has a really nice graphical meaning, which is adored. But, well, at least I adore it. It's a great graphical meaning. Now, look like this. Now we'll have to use the L'Hopital's rule, which is, I will Google it, don't worry.
I
I do understand the L'Hopital's rule. I am going to mess it up if I want to do it with a source. Using a source is just a good idea in general. This is the basic idea, but I do know that there is also... I'm pretty certain that's not the only thing. Should I give it... No, I shouldn't really add a proof to it. Why? Oh yeah, and also one other thing which I would like to do this stream, apart from calculus, at least partially calculus, because I don't think we'll get to partial differential equations or Fourier transforms. Yeah, but Fourier transforms, Laplace transforms are in the end, because actually they should be... That's a good point. They shouldn't be here. They should be over here. I feel like that's better, because Laplace transforms can be used to solve ordinary differential equations. Fourier transforms are kind of Laplace transforms juiced up. I know they are different, right? Obviously, but that's basically what they are. Fourier transforms are very similar to Laplace transform. See, if you take a look, Fourier transform, right, and Laplace transform. They have one different thing, because, yeah, 0 to infinity f of t e to the negative st thing, and Fourier transform, negative infinity to infinity, not a 0, f to the x, e to the negative I 2 pi. No, w is really often used here, if I'm not mistaken. I'm not good with Greek. Xi, oh, it's xi, okay, yeah, that's why I'm not good, it's xi. As you can see, 0 to infinity, e to the negative stt. Over here, it's negative I, 2 pi, w normally as a variable for this, and then x. They are similar, except Fourier transform is a bit more extreme. Over here, as you can see, there are no imaginary numbers, for example. Over here, they are. Also, you can divide Fourier transform into into a real and imaginary part in a very convenient way, and we will probably do it. For now, let's just go over to specimen time. I'm trying to do a stream in a bit of a different way. Recently, I'm having a few bad days, so I'm trying to do a stream in a very calm manner, which basically means not to rush anything, not force anything, just, you know, harmless fun. So another thing I'd like to do today is complete the tables. At least put things here. What are tables? Well, tables will be places for all of the definitions which are a bit too upsetting to just put over here. So, for example, over here we have, when it comes to medicine, for example, we'll have a definition of every single medical ward. And also we'll probably have a list of diseases later on and stuff like that, because that's defining every single word over here would be a pain, and it would just look terrible, it will be unreadable, so it's horrible, so we won't do that. In base abstraction, we'll put all of the derivatives, you know, table of derivatives for trigonometric functions, and table of Laplace transforms, table of integrals, and stuff like that. Because when you are solving these equations, it's really convenient to have them. Also, table of trigonometric transforms and everything that's beautiful in the world like this. When it comes to quantum physics, probably constants and also operators. Yup, when it comes to chemistry, well, every single atom. That's the way I'll probably do it. Okay. Now, let's get to it. So, L'Hopital's rule, very simple, base operation, and we have to get over here. There are no defined solutions for for x is equal to 0. 0. But if we take a look at the graph of the equation, then we can see that for values arbitrarily, that's not the right way to spell it, is it? Values, my goodness, I can't even spell values. Close to x equals 0, the function seems to return a reasonable value. Approach a reasonable value. That's why calculus is different from other. Actually, no. Limits are important. Compute, maybe. Using the I just realized how difficult I've made it for myself by using this example, as I'll have to calculate a sine of I'll have to calculate derivative of sine of x minus 1. Okay. Okay, it might actually not be as complex, but still will be more annoying than it should be. Which looks like this. And now comes for the awkward bit, because this will be limit as x right arrow c of fraction f of c divided by g of c is equal to, if I'm not mistaken, derivative of c g. Okay, is that correct? Limit, okay, limit, I forgot about the limit, obviously, I'm an idiot. There we go. Now, what are these equations? Well, these, that's why it gets awkward, are derivatives, about which tell you in the next subchapter. But for now, we'll just have to accept it as a rule. We will just have to accept it as a rule. Later on in the tables, we might also add all definitions. Oh, actually, I think I should divide that. Yeah. Oh, that's a good idea. Tables, and over here after the tables, we should have also definitions. Yeah. So we'll have definitions and tables separately. Okay. As rule, which means that if we know the derivative of both tables. Both sine of x minus 1 and x minus 1, then we can compute the limit. It would look like this. So comes the upsetting bit, because fraction actually d by itself, because I'm a professional, of a sine negative 1 is equal to, and then also by x minus 1. Obviously I'll calculate in Paint like a true scientist. I haven't done derivatives for months now, but if I'm not mistaken, f and g inside, the derivative of that would be equal to f prime g of x, g prime of x. Decently certain. Okay, let's see. Derivatives composition rule. Yeah, images, because obviously. Let's see. Oh yeah, I'm gaming. Oh yeah, I'm gaming. I am gaming over here. Cool. So now we have sine of x minus 1. And this would be equal to derivative of sine negative cosine. Oh my goodness, tables of derivatives are really, would really come in handy. Derivative of sine. Cosine, no, it's just cosine, okay. Yeah, whoops. So cosine, which means we'd have cosine of x minus 1. And times, this is just addition. Okay, so derivative of negative 1 is 0. Derivative of x is 1 times 1. Cosine negative 1. I haven't done derivatives for a while, so I would like to double check. Sine of x minus 1. It looks reasonable. So cosine of x minus 1. Yes, we are gaming. Okay, great. Cosine of x minus 1. And x minus 1, well, that's just 1. Yeah, it's equal to 1. Is equal to 1 always. Yeah, no matter what. Okay, which means that the limit would be equal to this entire thing, except divided by 1, and over here would be cosine, which means that it would be equal to cosine of 1, cosine of negative 1, cosine of negative 1. No, 0, I'm an idiot. Cosine of 0. Yeah, something wasn't right. Yeah, it's 1. Okay, that's true. I am an idiot. Give me a second. So this will be just 1. And based on that, we can just input the. This is fun. This is really fun. This limit is equal to 1 minus 1 which is equal to 1, which is equal to 1. There we go. And just like that, we solve the impossible. Now for other equations, what do I mean for other equations? One good example of that would be as limit of, okay, Wolfram alpha. That, I feel like that's the best place to actually put them in and double check myself, because it's Wolfram alpha. Limit as x approaches infinity. Oh, never mind, forgot. Wait, infinity? Dang it! Infinity of 1 divided by x. This, for example, will be equal to 0. But this is problematic because it's not really something you can... It's not really something someone can prove all by themselves. Just you know, whilst learning calculus or even rather advanced. It's not an easy thing to prove because it's a weird thing to even say. Because okay, it is obvious, right? But the problem is in math, things that are obvious are really often also not the things that are easy to prove. And because of that, I'm chucking them into the third category, because the only really way to prove it is to show that, look at this. Because most of you watching right now will be like, yeah, make it as obvious. Yeah, it is. But it wouldn't be as easy to prove as you think. Obviously, the one way to you can just show it, right? 1 divided by 10 is equal to, well, 1/10, right? 0.1. Right? Actually, I should do it differently. For x is equal to 10, it will be 1/10. For x is equal to 1,000, is equal 1/1000th. And you keep on going, and you showcase that every single time the x is increasing, this value is decreasing, which means as x will reach infinity, which means it will be large, well, very, very, very large, the number, as large as it can be, in fact, right? That's the idea of infinity. This means this number will be as small as it can be, which means it will have to be equal to 0. Smallest number, right? The smallest non-negative number. And that's kind of the proof, except it's a weird proof. It's, if you think about it, it's a logical proof, but if you compare it to other proofs, it is a weird one. And because of that, we just have to kind of remember that this is the thing. Now I just have to put it into words. There are some equations. You don't get oh, why are all these tabs to the left and this one isn't? Ah. There we go. There we go. Oh, because I didn't enter. Cool. Sending not know. One example of that would be, and over here we get NFT. I love the fact that Google has lighting like that. Oh, it's wonderful. Actually, X, I'm an idiot, sorry. Limit should be limit. That's X, right arrow, the T preferably, not an R, a T preferably, right arrow, infinity, this equation is rather standard. But we see that, well, actually, in theory, the L'Hopital's rule, we could use L'Hopital's rule over here, I suppose. Actually, it seems very easy to use L'Hopital's rule now I'm thinking about this, because derivative of 1 prime, I guess, would be 0. Derivative of x would be 1, which means we will get 0 divided by 1. I stand corrected. I stand corrected. This is actually... We can use L'Hopital's rule for this. Okay, so how about x squared? There we go. Now I solved the thing. Because now if we use squared, it's a different story. It's the same result, but it's a different story. Because if we use L'Hopital's rule, we'll get z. Okay, we shouldn't also get... Well, if we use L'Hopital's rule, it's actually the same thing. Fudge. Wait, but if we use... Whoa, that's off. There's something off. I messed something up. This is 1. Can you apply L'Hopital's rule to the... Wait. I don't think you can. Oh, if either... Okay, so yeah, you can't. You cannot. There we go. Yeah, something was off about it, because then x will have to go to infinity. So about the L'Hopital's rule, we forgot to add one thing over here. Before go any further, I would like to mention the limitations. Talking about limit is fun. Limitations of L'Hopital's rule. All right. You can only use it if, and it's this. Access as example. Okay, so we get either 0, 0 or infinity, infinity. Yeah, this is the only way to do it. Only if. Let's copy this limit. Maybe easier do it like so. F of x. By the way, what did I do C here? That's idiotic. There we go. F of x is equal to limit of g of x, which is equal to 0, or then we'll just copy this and just equal to plus minus infinity, right? But absolute value, that's the way they did it, I suppose. It's also reasonable. There we go. Infinity. Sick. Yeah. Of the first two rules apply here, because if we just insert infinity, we get 1 divided by infinity, right? That's Where's the... There we go. Now we can't due to the fact that not equals, because on the bottom we get infinity, on the top we get 1, so what are we supposed to do here? For it never seen before. If you look at it, if you look at all of these, well, standard definitions for calculus of these standard derivatives, you can see that the proofs of, like, the proofs are actually spectacular, just straight up spectacular, because it's really hard for most of them. For it never seen before. These things are usually more complex equations are really hard. There we go. Hi there, Elliot. How you doing? I did ping for stream. See, I'm different. Is my microphone? I know, you're the first person to join. It is. Great. Hi there. I'm doing muff stuff. English roll. Oh, good luck then. Nah, I'm setting you pass with flying colors. I mean, you did spend recently, but 6 hours speaking English, like, you know, without a break or anything. So yeah, it'll be fine. Still though, good luck. I'm sure you will need you'll crush it. Well, not complex over here. Yeah, I'm sciencing. I'm sciencing. Yeah, the science and stuff. I don't want to finish this paper because it's the first one that I actually would finish them. It's actually getting kind of large. I mean, it's getting rather massive. I really like to do some medicine, honestly. The only problem is that I cannot. It's really hard to do it on stream because I'll have to do it with a book, but without a book on screen. Oh my goodness, we actually did quite a bit. Actual tough, not complex, because complex is the second one. This is just tough. But not too high level. I could do presentation on. Oh buddy, welcome to the world of, okay, which transform? Which one would you like? Because both of these, if you take either one of these, you'll crush it. Okay, here are your two options. First one is Laplace transform. Very fancy L notation. It's, I don't know if I can even draw that L. Laplace transform, it's very fancy. Okay, it's just like this. Not in the program. Well, you have calculus in the program, right? Because technically this is just an integral. And it's a sick one. Yeah, because, I mean, Laplace and Fourier, is, if you were to, you know, make a presentation about them on the integral level, so just showing them off as an integral, well, that would be just mathematics applied. That's the problem with calculus. The problem is that all of this, real world use of all of this only comes in handy over here. Which is upsetting, because this is usually where, you know, schools stop. Which is so upsetting, because this is where all the juicy things go in. This is quantum physics, this is real, this is applied physics, basically. Ordinary differential equations. Well, yeah, but for example, when it comes to Fourier transform, you can expand it to get, let me show you. You can expand the Fourier transform. Maybe I shouldn't do it in Paint, maybe I should do it, just do it over here, because I will need it later on. When it comes to Fourier transform, you can expand it to the complex part and the real part. So negative infinity. It will be accepted. If this will get accepted, okay, if they will accept Fourier transforms, then that would be sick. Because, well, I already expressed my love towards Fourier transforms. Basically, the thing is, every single thing you've learned about calculus is a setup, basically. These are the things that you need to learn in order for calculus to be useful. And this is calculus being useful. And not in the program. But I mean, in theory, they are just an integral. Right? You do know what differential equations are, right? Because then I can do you a quick introduction to Laplace transforms to maybe. Like a really quick one, because I'm also not experienced now. I haven't written the thing yet, so just in case you don't, because whilst we're waiting for the answer, I can yeah. So when you have a differential equation, like for example, okay, maybe I've gone a little. Oh yeah, there we go. Plus y is equal to. Okay, so a really quick introduction. Gotcha. Basically, if you take the Laplace transform of this, if you take the Laplace transform of this, you can convert it after some. Okay, over here you have 3 dots because there is a bit of math here. Applying the Laplace transform and stuff like that, you can get it to a thing where you only have y's. You don't have any y parameters. So you don't have any no derivatives. You only have y is equal to ... That's the idea behind Laplace transforms. You apply them, then you do some extra math. You apply them, you do some extra math over here, and then you basically have the equation solved. That's the Laplace transform. On the other hand, Fourier transform, as I explained before, that's the sine thingy. And this is it. Laplace transform is just a single integral which has no imaginary parts. Only e to the st f of t dt. Looks like this. That's Laplace. From 0 to infinity. And as you can see, you apply them, you do some extra math, and you finish this. That's a suggestion. Yeah, that's from me. But if you need something else, I could also think maybe I'll find something from quantum physics, for example, something that like this or something like that. So there you go. Good luck, Elliot. That was actually a really quick introduction to Laplace transforms. I really like the idea of building Laplace transforms up from the ground. That's really fun. See ya, adios. Okay, what a joyful lad. Oh, I should charge my phone. Just 4%. If I won't be able to accept any phone calls, then it won't really make a difference, and no one really calls me. Okay, so except for my bank, but no, they just are mad because they lent me some money and now I have to give it back. Just cringe. Actual tough examples might be a tad more complex than this. Should give you a feel for in here. There we go. Now, epsilon delta definition, beloved by everyone. I will definitely not do epsilon delta from memory because it's pointless to memorize epsilon delta definition. I know what epsilon delta is, and that's actually very handy, and you should know that too if you want to do calculus. I would advise you not to memorize the epsilon delta, but know what it means. Which basically, I never remember actually even which way epsilon delta is. Which is epsilon, which is delta. I just remember what it means. It basically means that if you have a function, it is check if it is continuous, basically. That's the basic idea. If you have something like this, distance from the point of interest, like whatever, epsilon. I'm doing it totally wrong, aren't I? Well, we don't actually care about it, yeah. Then this thing will get only delta. I should do it probably, shouldn't I? Oh, I have -1 viewer. Wow, that's impressive. Yeah, so I could do it in Manim. The same, there are so many explanations of that already in Manim. Not as an animation Manim, only as graphics, because that's a very convenient way to make those graphics. Over here I somehow made up, I somehow created this, which is a white background Manim. Alright. So damn, I'm tired. I shouldn't be. I'm just gonna move on the videos today. I don't even know which ones. It's a good question. Let me just open up. I'm sort of stopping the stream for a second, but recently I've been having a bit of a down week, so it's hard to kickstart my walk-on videos. Scripts. What fun video do I have unfinished? Well, a couple actually, a lot. What fun video which I could finish? I think I'm back to weekly uploads. Yeah. I did love them shorts, and yeah, it's painful. Selling your soul. Shorts by themselves is kind of easy, but it's a bad feeling of selling your soul. I don't like it. But when it comes to integrals, I didn't divide it into what are integrals and computing integrals because, well, actually, maybe I should do computing integrals because there's a way to compute integrals. Over here should be calculating derivatives and computing integrals. Calculating derivatives, and over here it should be what are integrals and computing integrals. There we go. Alright, I feel like I should go get more on the video. So for that will be it. This short stream, we didn't do much, but it was chill and calm. Thank you so much for watching and have a great day. Bye!